Okay, similar and congruent solids. I'm doing this video by myself, no videographer. Let's see how this goes. So earlier this year we talked about similar polygons. Polygons where all corresponding angles are congruent and all corresponding sides are proportional, or in plain English, same shape, but they don't have to have the same size. There can be a scale factor where every side becomes 3 times bigger or 1/4 as big. Same idea with similar solids, three-dimensional figures. So if I have two right rectangular prisms, like these two boxes, and if all the corresponding one-dimensional lengths are proportional, if I get equal ratios, then we would say that they're similar. So here it's very easy to see, since 5/10 is 1/2, 7/14 is 1/2, 4/8 is 1/2. These are similar rectangular prisms, and the scale factor is 1:2. Now, I'm going to jump right into an example of something to get to the point of what this is really all about. Now this prism, we have choices about which surfaces we want the bases to be. It could be the front and back are the congruent parallel surfaces, could be the left and the right, or it could be the top and the bottom. Let's say the top and bottom are the bases. So this is one of the bases of the prism, just so we're all looking at this prism the same way. And on this one, this would be the corresponding base on the large prism. And here's what I'd like you to try to do. Grab your calculator. For each one, can you figure out the perimeter of the base, which I shaded, the surface area of the prism? Now, we haven't done the surface area chapter yet, and there is a formula, but for now I'll just tell you what it means and you can figure it out. The surface area of that prism is the total area of all surfaces. So get the area of the bottom, the area of the front and the right side and the top and the back and the left, and add them up. That's your surface area. And can you get the volume of this prism? And then do the same thing for the large one, perimeter of the base and the surface area and the volume. Now notice all of the dimensions doubled, right? Every length, width, and height over here is twice as big as those. So let's see what happens to the perimeters of the bases and the surface areas and the volumes. So you can hit the pause button and try that. All right, so the perimeter of this base is just 7 plus 4 plus 7 plus 4. So that's going to be 22 meters. The surface area, well, let's see. The bottom surface, 7 times 4, 28. The top surface, 7 times 4, 28. The surface on the left is a 5 by 7 rectangle, so that's 35. Surface on the right is 5 by, the front was 5 by 7, 35. And the back is 5 by 7, 35. The surface on the left, this surface is a 5 by 4, 20, and the surface on the right is 20. So if we add those up, we get 166 meters squared. Now, there is a faster way to get surface areas of prisms that we'll learn about in chapter 12. Volume, area of base times height. So the base is a rectangle of 28 meters squared. We have 5 layers of that base, 5 meters on the height there. So 28 times 5, 140 meters cubed. So those are the answers for the small one. The big one, perimeter of the base, 14 plus 8 plus 14 plus 8, 44 meters. Surface area, so the bottom rectangle, 14 times 8, plus the top rectangle, 14 times 8, plus the front rectangle, which is 10 times 14, plus the back rectangle, 10 times 14. The surface on the left is 10 by 8, and the surface on the right is 10 times 8. If you add up all 6 areas, you get 664 meters squared. Volume, area of the base, so 14 times 8, and then you multiply that by the height of 10, and we get 1,120 meters cubed. All right, so what's the point? Remember, all the one-dimensional lengths doubled. 7 times 2, 14, 4 times 2, 8. Is that what happened with these measurements? Well, perimeter is a one-dimensional measurement, and it did double. It was 22, it's now 44. But look at the surface area. It didn't double. 166 times 2 is not 664. It actually got 4 times bigger. And the volume did not double. 140 times 2, that's not 1120. That's actually 8 times bigger over here. So let me zoom in a little bit, do some more writing. So here's what's going on. If we make a ratio of these perimeters, it would be 22 over 44, which is 1 to 2, which is the scale factor. 1 to 2. If we make a ratio of the surface areas, that would be 166 over 664. That simplifies to be 1/4. I'm going to write 1/4 a strange way. 1/4 is equal to 1/2 squared. And I'm writing it that way because 1/2 is a meaningful number regarding these two similar prisms. 1/2 is the scale factor, so it's the scale factor squared. Ratio of volumes, 140 for the small volume, 1120 for the big volume. And if we simplify that, that's exactly 1/8. And I'm going to write that a strange way. 1/8 is exactly equal to 1/2 to the third power, 1/2 cubed. In other words, the scale factor cubed. So here's a summary of what I want you to get from that first little activity. Get a good shot of this. For similar figures, similar solids, three-dimensional figures, a ratio of the perimeters, or if they were cylinders or cones, a ratio of the circumferences of the bases is always going to equal the scale factor. But if you make a ratio of the surface areas, it's always going to be the scale factor squared. And a ratio of the volumes will always be the scale factor cubed. So we'll do some examples in a moment, but this little list here is what the whole lesson is about. And the previous example that we just finished is kind of showing you where this information comes from. So let's look at a few examples. One kind of problem I'd like you to be able to do is, zoom out a little bit, is this. Are these pyramids similar? So I drew two right pyramids, same type of pyramids, they both have rectangular bases. It's not like one's got a triangular base and one has a hexagonal base, those wouldn't be similar. But these could be, they're the same type of shape. So are they similar? Well, we'd have to check our ratios. So let's see, the heights are 6 and 15. So 6 to 15 is 2 to 5 when we simplify it. 8 over 20, if you simplify that fraction, that's 2 to 5. And so there's 8 over 20. What's left? Oh, this length compared to that one. 3 over 7. No, that's a different number. That's not 2 to 5. That's just 3 to 7. So because all the corresponding lengths are not proportional, these are not similar. This ratio and this ratio are equal, but that ratio is different from the other two. These are not similar polygons. So they can only be similar if all the dimensions are changed the same way, by the same scale factor. If you look at this bowl here, if I got a smaller version of that bowl that was half as tall and half as wide, it would be a similar bowl. But if I got a bowl that was half as tall and 1/3 as wide, it would not be a similar bowl. It would have a different sort of look to it. So that's the idea. Let's try another one. All right, so go back over here. And I can zoom in a little, it looks like. So you'll have some homework problems that look like this. They'll give you two solids, and instead of asking you if they're similar, they might tell you they're similar, or in this case, we know they are. Just like all circles are similar, all spheres have to be similar. All spheres have the same look to them. So the question is, what's the ratio of the surface areas and what's the ratio of the volumes? Now, listen carefully. If you have no life, you heard me right. If you have no life, what you could do is you could look up the formula for the surface area of a sphere, and you could figure out this surface area, and you could figure out this surface area, and you could make a ratio of your two answers and simplify it, and you will get the right answer. Or you can remember this piece of paper from earlier. So we see the scale factor, 12/18. Scale factor comes from a one-dimensional length compared to the corresponding one-dimensional length. So the scale factor here is 12/18, or 2:3. That's the scale factor. So the ratio of the surface areas is going to be the scale factor squared. 2 squared is 4, 3 squared is 9. The answer is 4:9. So that's not telling us what either surface area is. That's telling us if we knew the two surface areas and compared them to each other, it would be a 4:9 ratio. So same thing here, ratio of volumes. If you have no life, you could use our volume formula. Get the volume of this one, get the volume of this one, put them in a ratio, simplify. You will get the right answer. Or you can remember the ratio of the volumes, as we saw from our first example with those two rectangular prisms, is the scale factor cubed. So all we have to do here is the scale factor cubed. So 2 to the third power is 8, and 3 cubed, 3 to the third power, is 27. That's the ratio of the volumes. All right, finally, this one. Let's see. These two, I'm going to frame this shot a little bit, give me a second. These two solids, cylinders, are similar. So I'm telling you they're similar. So maybe you can pause your video and see if you can get these 5 answers. If you can do these 5, you're probably going to do a great job on the homework. The last one is the sort of extra challenging one. All right, so scale factor. Well, scale factor is a ratio between two corresponding one-dimensional measurements. So in this case, the scale factor is going to be 9:6. So always simplify, so 3:2. The height of one over the height of the other. Then I ask for the ratio of the diameters. Well, diameters are one-dimensional measurements, just like perimeter, just like height, just like length and width and radius. That's a one-dimensional measurement. That's going to equal the scale factor. Just like on our very first example, I'm going to put back in for a moment. The perimeter of the base was 22. Perimeter is a one-dimensional measurement. We don't measure in meters squared. Perimeter is just a measurement of, say, meters. And the corresponding one was 44. That's a one-dimensional measurement. And when we made that ratio, it equals the scale factor. So the answer to number 2 is the same as number 1. It's going to equal the scale factor. 3:2. Ratio of the surface areas. Well, since they're similar, it's just going to be the scale factor squared. So that's 9:4. Ratio of the volumes. Well, since they're similar, that's just going to be the scale factor cubed. So what's that? 27/8. And now the bonus question. Bonus extra credit question worth 0 points. Let's see how we did here. If the volume of the large cylinder is 540 pi, what's the volume of the small cylinder? Here's how we can, the answer is 160 pi. Here's how we can figure it out. It has to do with using the answer to number 4 up above. We already figured out what the ratio of the volumes would be. If we knew both volumes and we made a ratio out of them, that ratio we said would be 27/8. So there it is. The big volume compared to the small volume is going to be 27/8. It doesn't mean the big volume is 27. It doesn't mean the small volume is 8. But if we made a ratio out of them and simplified, that's what we get. So let's do it. Let's make a ratio out of the 2 volumes. The big volume, we know, 540 pi. The small volume, we don't know. So there's my variable. So I cross multiply 27 times volume of small equals 8 times 540 pi, which is 4320 pi. And then I just divided both sides by 27 to get the volume of the small is 160 pi. All right, so it's going to be very interesting on Google Classroom when I look at your homework so I can figure out who has no life. And if you watched the video and listened carefully, you'll know exactly what I mean. Have fun.